Good morning, Professor. Good morning. How's it going?
Doing well. How about yourself?
Good. I'm good.
All right, it's 8:30. Let's go and get started. All right, good morning, everyone. How's everyone doing today? Doing good, doing good. I had a Super Bowl party over the weekend, but you know, a lot of my friends aren't really into football, so I was texting a bunch of my friends last week and asked if they want to go to the Super Bowl, and they all basically gave me the same kind of variation of the same response. Like, I'm not really into football, but I'll come over to your house and eat your food and watch Rihanna. Ended up being kind of just a Rihanna watch party and just people just eating my food. It was still fun. It was still fun to hang out. And, you know, always good to get my friends together. But you know, hope you guys had a good weekend too. Okay, so today is starting a new thing. So you know, I think for the first 3 weeks, we've been doing mostly review of ordinary differential equations. Today we're starting something new. So we're going to be learning a technique called Laplace transform. So this is going to be basically our topic for the next 3 weeks, and this is going to take us right up until the first midterm. All right, so announcements. Homework 2 is out there right now. I know I made some mistakes on the solution, and I apologize for that. So if you're getting any different solutions to the homework than what I have posted, please let me know. You know, because you know, for all these homeworks, I basically make them up from scratch, and I try to get the solutions done quickly just so I can get the problem done. So Sometimes, I do make mistakes on the solutions, and so if you're getting something different than what I have posted, you're probably not crazy, probably. And so it could be that I just made a mistake on just let me know, and I'm always happy to take a look again and, and correct it. So I apologize, I don't do it on purpose. I know there in the past people have had conspiracy theory that I do these on purpose, that maybe connected more. That's not true. I really do try to make them all right first, but sometimes when you're going fast, it's hard to finish everything right. Okay, so that's all my announcements. Are there any questions I can answer before we get started? Okay, all right, so let's go ahead and start the lecture for today. And today will be an introduction to Laplace transforms. You guys haven't seen Laplace before, right? So I don't think they covered this in that. It's probably everyone's the first time. All right, good. All right, so for the first 3 weeks, we've been covering ordinary differential equations, just because of their importance in engineering. Okay. But what we've seen is that when you're solving a differential equation, it can be somewhat of a tedious process, especially once you get to the second order ODEs, the initial conditions and non-homogeneous, right? So solving ODEs can be pretty tedious, at least in my opinion, it can be pretty tedious. And I think what's especially tedious about solving ODEs is that you have to remember a lot of different solution steps. And so just think of kind of what we ended with last week, right? And so if you have a second order ODE with initial conditions and non-homogeneous terms, you have to solve it in kind of 3 steps. So first you have to solve the homogeneous problem. Then you have to solve the non-homogeneous. You undetermined coefficients, which by itself is already kind of a hassle. And then once you're done with all of that, then you apply the initial condition. So it's kind of almost like you're solving 3 problems in one, and kind of in the worst case scenario. Okay, so that could be pretty. But due to their prevalence in engineering physics, there's going to be a lot of ODEs that you're going to be seeing in a lot of your different classes down the road, namely the vibrations course and or heat transfer. Some of you may be in heat transfer. And so basically, what people thought is, there must be a better way to solve these differential equations than going through that tedious process. Okay? And one of the bigger issues that's there is that when you're solving these differential equations normally, you're kind of constrained in the what I call the physical domain. Okay? And what I mean by that is that when we have these differential equations, and they often are used to represent kind of physical problems, our independent variables are things like x and things like t. So these are kind of physical things, right? They're either space or time. Okay. Mostly just because that's just how these equations are defined. So oftentimes these come from equations of physics, and those equations of physics are. And so, one person, I'm guessing his name is Laplace, sometime down the road said, what if we perform a change of variable and put the differential equation in a form that's easier to solve? Because if we're kind of smart, if we're kind of clever with our changing variables, we can transform a differential equation into a form that's, you know, a lot easier to solve, maybe an algebraic, right? Algebra generally is easier to solve than differential equations. And so, you know, if we choose our transformation or we could design it in a way that allows us to do algebra, you know, that we can solve these differential equations easily, at least in theory. And so this change of variables that this person came up with is called the Laplace transform. And so today, you know, what we're going to do, so this is kind of the overall goal. And so, you know, even though maybe I kind of tricked you guys a little bit at the beginning. So even though I said we're moving on from differential equations, we're not really moving on. We're just, you know, learning a different way to solve the differential equations. And you know, you may be wondering, you know, kind of why are we doing this? Why are we going through this trouble of learning a whole different way to solve differential equations when we already have that? So everything that we learned in the first 3 weeks, all of those are completely valid. And so the Laplace transform kind of has two distinct advantages. On the one hand, you know, when you use the Laplace transform to solve a differential equation, your problems are solved a lot more directly. Okay. And so what you'll see, you know, as we do the example, maybe not today, but probably on Thursday, when you have things like initial conditions and non-homogeneous terms, all those are kind of solved together in the same step. And so that's kind of a nicer way to solve these problems, and to kind of solve, you know, like 3 separate problems like I was talking about. But when you do Laplace transform, you kind of transform the entire equation all at once, and the initial conditions are factored into that transform. Okay? And then, you know, it all kind of comes together all at once. And so it's in some sense, you know, it's a little more satisfying, but you know, that's also kind of up to subjective as well. But the advantage number 2, and I think this is the real advantage, the real reason why people use Laplace, is that it allows us to use different kinds of forcing functions or different kinds of non-homogeneous terms. And so in particular, you know, we're going to focus on 2 in this class. Probably not this week, we'll probably get into it sometime next week. And they're called step and impulse. And so we'll talk about what step and impulse functions are and why they're useful. Because you know, a lot of engineering you know, systems, you know, a lot of times we like to use these step and impulse functions just because they model physical behavior very well. Okay, so being able to use those in combination with the differential equations is something that's going to be really useful for us. All right. And so, you know, you're probably wondering, you know, how exactly are we going to use these transforms? We talked about kind of why we're using it, what their advantages are. So every time you solve a differential equation with Laplace transform, it kind of follows the same framework. I think, you know, I have this kind of flow chart here. kind of show it. Right, and so you're going to start with the physical space ODE, and so this is basically the same starting point that we had before. Okay? And so, for instance, maybe we have our mass spring damper. And so we have a differential equation where the independent variable is time. Okay, so our starting point is the same. And then from here, we're going to apply a Laplace transform. And what that's going to do is that it's going to transform our differential equation from the physical space into the Laplace space. Okay? And so instead of basically, we're going to change the variables, in this case, from t to s, which is Laplace space. So you want to get something like this. Okay. The important thing is that through the Laplace transform, we're not going to have any derivative in it. So our Laplace space equation will be purely an algebraic equation. Okay. Then once you have your original equation in Laplace space, then you're going to perform algebraic manipulations. And so you would solve this as if it were just a regular algebra problem. Okay? So you're basically solving for y of s in this case. And so what you obtain from that is the Laplace space solution. And so we're solving for something like y of s. And then once you have the solution in the Laplace space, then you have to transform that back into the physical. So, the Laplace space is nice, it's convenient for us for solving problems, but the Laplace variable doesn't really have any physical significance. So usually when we want to interpret the results, when we want to plot them or to use them for analysis, we often need to transform it back into the physical. Okay, so we're going to perform kind of the inverse operations. We call that the inverse Laplace. Okay. And if we perform the inverse Laplace, what we obtain from that is the solution back into physical. Okay. All right, so that's kind of the roadmap of kind of where we're going. Okay, so and we're not going to do this all today because there's kind of a lot to learn. So today, we're focusing mostly just on this part. And so we're going to focus on taking, how do you take a function or a differential equation and how do you perform that in Laplace? Just because I think this is probably the first time most people are seeing the Laplace transform or just an integral transform in general. So I want to make sure that we spend some time. We look at a ton of examples today of how to perform this transform. So that when we get to solving those E's, then it becomes kind of a second. All right. Any questions on any of this so far? Okay. All right. So let's actually introduce what the Laplace transform is and what it actually looks like. Okay. The Laplace transform is a type of transformation we call an integral transform. The reason we call it that is to perform the transform, we have to perform an integral. And just like I mentioned before, the purpose is to basically take our usual variable, which is either x or t in most cases, and then we're going to basically integrate that out. So by performing the transform, our variable will become s, which is the Laplace theorem. And so it looks like this. So the way that we basically denote that we make kind of a fancy L. That's fine. And that fancy L is going to be applied to some function f of t. Okay? And so this kind of notation right here means the Laplace transform of f of t. So f of t is just some function. It could be almost anything. And then when we take the Laplace transform, it kind of looks like this. So the Laplace transform is an integral. We integrate from 0 to infinity of e minus st multiplied by f t d. And so by performing this integral here, you can see that t is our integration variable. Right? So that's the one that we're integrating over. And whenever you integrate over a variable, that variable, remember, disappears from the equation. Right? And so what we can say here is that the variable t integrated. And so after performing this integral, t is no longer going to be in the equation because you basically integrate it out. And then once you perform that integral, your function now is going to be a function of s, right? Because we have this s here in the exponential terms. Okay. And so by performing this integral, t is going to go away, but then we're going to be replacing it with a function of s instead. And then usually the shorthand for it is that we call it a function f, big F of s. So that's kind of the notation I'm going to be using for this section. So if it's a lowercase function, lowercase f of t, that's usually going to be a function in the physical domain. But if I use an uppercase for the function name, like big F of s, that's going to be a function in the Laplace. Okay. I'll usually try to put like parentheses t or parentheses s. I'll try to do that as much as I can, but in case I don't, that's kind of what I mean by it. Okay. All right, so let's do a couple examples of that so we can kind of see this. All right, so let's start very simple. So let's start with an f of t that's just a constant. So let's say f of t is equal to 1. Okay. So let's find this. Let's find the Laplace transform of a constant. So basically, we're going to be finding the Laplace transform of 1. Okay. Let's go ahead and plug it into this equation up here. So we have integral 0 to infinity e to the minus t. F of t here is just 1 dt. Okay. So the one is just a constant, and so, we can almost kind of neglect it, I guess, in the integral. And so we're taking the integral of e to the minus st. And so we take that integral, we get minus 1 over s times e to the minus st. Okay. As integral of an exponential is just the exponential, but because of the, I guess, the inverse chain rule, we get a minus 1 over s out front. And we're going to evaluate this from 0 to infinity. We don't need any arbitrary constant here because we're performing a definite integral. And so since we have bounds on the integration, there's no need for the arbitrary constant. So you don't have to worry about that anymore. Okay, so let's go ahead and apply our bounds. We have minus 1 over f times e to the minus infinity minus e to the 0. E to the minus infinity, of course, is going to asymptote to 0. Okay, so we can ignore that. And e to the 0 is just 1. Okay. And so what we have for the Laplace transform is we have minus x times minus 1. We multiply those together and get 1 over that. And so the Laplace transform of 1 is just 1 over x. Any questions on this example here? Right. So this, I think this result is a little bit strange when you kind of think about it, right? And so we start with a constant function. We start with just 1, so there's not even any time where there's no space of fitting at all. But by performing this Laplace transform, this s kind of almost appeared out of nowhere. So it is, I think that part is a little bit strange, but we're going to utilize this, going forward. Okay, let's do another example. All right, so let's find the Laplace transform. Let's find the Laplace transform of f t is equal to e to the a. Okay. So it's a simple exponential function in the physical domain. All right, we're going to find the Laplace transform of e. Okay. Let's go ahead and plug into our formula here. So we have the rule into infinity e to the minus st times f of t. F of t in this case is e to the at. E. We have two exponential functions multiplied by each other with the same, same variable on top, which is t, and so we can kind of combine these together into one exponent. I'm going to do it. Okay. And so we combine their exponents to get e to the minus s minus a. All right, so let's go ahead and perform this integral. And so if we perform the integral, we get minus 1 over s minus a multiplied by e to the minus s minus a t evaluated from 0 to infinity. Right, so our integral is very similar to the previous example, except instead of dividing by minus 1 over s, we divide by minus 1 over s minus a. Let's go ahead and apply our integration bounds. And so just like the example above, we have e to the minus infinity minus e to the 0. And so e to the minus infinity just goes to 0, and then e to the 0 just becomes 1. And so we have minus minus 1 over s minus a times minus 1. We have those two negatives that are just going to cancel out. And so what we have is the Laplace transform of e to a equal to 1 over s. Any questions on this example here? Yeah. All right, so not so bad so far. So we did a couple fairly simple examples, but hopefully this is kind of making it seem a little bit less scary. I think usually when you say change of variables, people get a little bit nervous because it can be kind of a tedious process, but Laplace transform is not too bad. All right, so let's take a break from the examples. I do have quite a few more examples to cover today, but I did want to take a break to talk about linearity. Okay. So the Laplace transform, as we've defined it so far, is a linear operator. And the reason for this is because integration, which is the primary operation that we're performing from Laplace, integration by itself is already linear, and we didn't really introduce any nonlinearity. So this is really nice because for a linear operator, there's a lot of really nice properties that we can take advantage of for that linear. And so let's say that we have two functions, f of t and g of t, so they can be totally different functions. And let's say that we have two constants, and so a and b. So a and b are just just numbers or just scalar values. If we take basically a linear combination of f and g, and we try to take it to Laplace transform, the resulting Laplace transform will just be the individual Laplace transforms of f and g. Okay, let me finish that. And so let's say that we kind of formed a super function here, which is a f of t plus b g of t. Okay. And so we're basically taking a linear combination of this two functions. And let's say that we want to take the Laplace transform of this entire thing. And so we're taking the Laplace transform of the linear combination of f and g. Because Laplace transform is a linear operator, if we multiply it by a constant, the constant is just going to pop right up. And so the constant doesn't affect the Laplace transform at all. Okay. And so a is just going to pop right out. And we can take the Laplace transform of f of t, okay, just by itself. And then the plus sign, because of the linearity, that can also kind of be, popped out as well. So we have e transform of So this is really nice here. And so, if we wanted to take the Laplace transform of, of a combination of functions, then we can just, instead just take the Laplace transform individually. And we're going to use this in clever ways too, because what we'll see is that, we're going to have functions that may look very complicated in terms of, adding a bunch of different terms. But if you can break it up into terms that may look similar, maybe Laplace transforms that we've done before, kind of simplifies the process and makes it a lot easier to solve. Okay. All right, so let's see this in action. Let's do another example. And so this time, for this example, I want to find the Laplace transform of hyperbolic cosine. Okay. And so our function this time is hyperbolic cosine. So if you haven't seen it before, it's basically cos h of the cosh. All right. And so hyperbolic cosine, that's just kind of a fancy way to state this function. So hyperbolic cosine is basically 1/2 times e to the at plus e to the minus t. We basically have the sum of two exponential functions. And so, between hyperbolic cosine, that's just how hyperbolic cosine is defined. So if you haven't seen it before, this combination of exponentials appears, somewhat often in applied math, and so people just decide to give it a name. So that's hyperbolic cosine. Okay. But if you want to make it a bit simpler, basically what we're solving for is just, what's the Laplace transform of 1/2 e to the at plus e to the minus at. Okay. All right, so let's go ahead and do this. And so we want to take the Laplace transform of 1/2 e to the at plus e to the minus at. Okay. So this looks, like it would be a bit complicated. So if we want to do this, the same way we did our first two examples, we would plug in 1/2 e to the at plus e to the minus at back into our integral transform. But let's do it a bit more intelligent. So let's use the fact that this Laplace transform is linear. So let's use linearity. And so if we invoke linearity, that 1/2, which is just a constant, that's just going to come out. And so you don't have to worry about Laplace transforming that. Then we can apply Laplace transform to each term individually. So we have the Laplace transform of e to the at plus Laplace transform of e to the minus at. And so this is great right here because we have a Laplace transform of two exponential functions. And if you go back in time like 10 minutes, you can see that we've already solved this, right? We've solved that the Laplace transform of an exponential function is just 1 over s minus a. And so let's use this. So let's not bother going through the integration again because we've already done this. And so if we plug in our Laplace transform for e to the at, we'll get 1 over s minus a. And then the Laplace transform of e to the minus at, we can just use the exact same transform, but instead of a, we plug in minus a. So that ends up being 1 over S plus. Okay, so technically you're done, and so this is the Laplace transform. So we've successfully taken out the t, replace it with s. But we can kind of clean this up a little bit just to make it look a little bit nice. So what I'm going to do is I'm going to basically get them under a common denominator, and so I'm going to multiply the first one by s plus a over s plus a. Second one I'm going to multiply by s minus a over s minus a. And so I'm going to say common denominator. And so if we do that, then what we get is, then I think we get the two. The 2 is going to cancel out with something on top too. We get 1/2. The common denominator in this case is s squared minus a squared. And then in the first one, we have s plus a plus s minus a. Two a's are going to cancel out because we have a plus a and a minus a, and then we have a 2s up top. And so the 2s is going to cancel out with that 2. And so we have s over s squared minus. So that is the Laplace transform of hyperbolic. All right, any questions on that example? All right, so linearity is really nice, and so we're definitely going to be making use of that a lot in this class, because a lot of times we're going to be looking at combinations of functions, especially when we're looking at things like differential equations and not homogeneous terms. And so definitely remember linear. It's going to help you out a lot. Okay, next example. All right, and so the next example, we're going to look at the Laplace transform of both sine and cosine. So this is something that can be really useful for us, because if you remember from our solution to ODEs, especially the second order ODEs, we had a lot of solutions that had sine and cosine. Okay? And so there's really no way to avoid it, and so we're going to have to do this eventually. So let's see what their Laplace transform look like. And I'll give you a hint that this process is going to be very similar to homework 1. Where we're going to be doing integration by parts. All right, let's go ahead and do it. The Laplace transform of cosine omega t. Let's go ahead and plug that into our formula. Okay. And so we plug into the formula, we get integral from 0 to infinity, e to the minus st times cosine omega t dt. Of course, we're going to have to integrate this by parts. So for the u, we'll say that's equal to 4 times t. And du is going to be the derivative, so we have minus omega t. And dv, we're going to have the other part of the integral, so that's e to the minus st t. So we take the antiderivative of that, we get 1 over s e to the minus s. All right, so let's go ahead and perform our integration by parts. And so we're going to multiply these two together. The plus sign, and then we're going to multiply across with a minus sign. And when we go across, remember we have to apply an integral here. Okay. All right, let's go ahead and bring it down. We have the Laplace transform of cosine omega t. This is equal to minus 1 over s e to the minus st cosine omega t. Okay. So that was the result of the diagonal multiplication. And so there's no integral on this, and so we can basically apply the integration method. So from 0 to infinity. And then we have a minus, and so three minuses actually, right? We have minus here, minus here, and minus here. So in the end, we get just a minus omega over s. And we go from 0 to infinity, e to the minus st sine omega t. Where you'll notice I factor the s and the omega out of the integral because they're not part of it, right? So our integral is in t, and so since our integration variable is t, anything that's not a function of t, we just pull out. Okay. Okay. All right, so let's so we have a couple terms to evaluate here. So let's start with the term that's not the integral. Okay. So minus 1 over s times. And so I'm gonna apply the integration bounds of infinity and 0 to what's inside the, the e to the minus st times cosine. If we have e to the minus infinity cosine of infinity minus e to the 0 cosine. So this was basically the result of, all I did was just apply the integration bounds to that term. And then we have the integral term. So the integral from 0 to infinity, e to the minus st times sine omega t dt. Okay. If we kind of look at this, and if we were to apply, we're going to do that very soon. And so, if we were to apply the Laplace transform of sine, that's exactly the equation that we would get, right? And so that term right there, that integral, is just the Laplace transform of sine omega t. All right, let's simplify this a little bit. And so, for the first term there with the cosine, we have e to the minus infinity times cosine infinity. Due to the decaying exponential, e to the minus infinity, that's going to be 0. Okay, so we can ignore that term. Whereas the second term here, e to the 0 times cosine 0, okay, you evaluate both of those functions at 0, we end up with 1. And so we get a minus 1 over s times minus 1, and so we get a positive 1 over s. All right, so let's go ahead and kind of write it all down into one equation. So we have the Laplace transform of cosine omega t is equal to a positive 1 over s minus omega over s, Laplace transform of sine omega. All right, and that's basically about as far as we can take this one. All right, any questions on any of the work that we did for this example? Okay. All right, so we applied the Laplace transform to cosine omega t, and we got this. It's not really that satisfying because we have two Laplace transforms here, and we can't really explicitly solve for them. So we're not done yet. Okay? And so the next thing we're going to do is we're actually going to compute this Laplace transform with sine omega t. And then what we'll get is we're actually going to get a second equation that relates sine and cosine together, and then we're going to solve both of those at the same time. Let's take the Laplace transform of sine omega t. And so that's integral 0 to infinity e to the minus st sine omega t Just like before, we're going to integrate by parts. All right, so I just went a little bit quickly just because it's almost a repeat of what we had before. But basically, we choose the u term to be the trigonometric term, okay? And we choose dv to be the exponential. So we get that. And just like before, we're going to perform our multiplications across our integration by parts. And so we have sine omega t. Laplace transform of sine t equal to minus 1 over s sine omega t, evaluate from 0 to infinity. Derive e to the minus st in a minute. E to the minus st. T evaluate from 0 to infinity plus omega over s, just like before, integral 0 to infinity e to the minus st cosine omega t So let's go ahead and simplify this. And so let's take our e to the minus st sine omega t and apply our integration down to that. Okay. So you have minus 1 over s times e to the minus infinity sine of infinity, okay, minus e to the 0 sine of 0. We know e to the minus infinity multiplied by almost anything is going to be 0. Next, we have e to the 0 times sine of 0. So e to the 0 is just 1, but sine of 0 is 0, right? And so this is also going to be 0. And so this entire first term right here is just not going to exist. Okay, so everything there is just 0. And then for the second term, we have omega over s, that's still going to be the same. And then we have integral from 0 to infinity, e to the minus st times cosine omega t dt. And of course, this is just the formula for the Laplace transform of cosine. Okay. And so if we simplify this out, what we get is Laplace transform of sine omega t equal to Laplace transform of cosine omega t multiplied by omega over s. Right. Any questions on how we did this integration here? All right, and so we have two equations here, both of which, neither of which are very satisfying because they both involve two Laplace transforms. But if we take these two equations, okay, let me zoom out so you can see both. Okay, we can solve them together at the same time to basically obtain our, Laplace transform, our actual Laplace transform of sine and cosine. So if I call this equation 1 up here, we call this equation 2 down here. We just have to solve them basically simultaneously. All right, and luckily, this system right here is not too difficult to solve, because what we can do is if we look at equation 2, equation 2 gives us an explicit expression for the Laplace transform of sine omega t. So let's go ahead and plug that directly in to this equation up here. Plugging 2 into 1. What we get is Laplace transform of cosine omega t is equal to 1 over s minus. We have omega over s times omega over s, so that's omega squared over s squared. Laplace transform of cosine omega t. And now that we've done this, we're in luck because the only unknown that we have here is Laplace transform of cosine omega t. Right? And so we can basically solve this equation algebraically for that Laplace transform. All right, I'm going to take this term right here. I'm going to take this term and I'm going to move it to the other side. And so we do that, we get 1 plus omega squared over sine over s squared. Times Laplace transform of cosine omega t equal to 1 over s. I'm going to divide both sides by this factor right here. And so we divide by that factor, we get Laplace transform of cosine t is equal to 1 over s times 1 plus omega squared over s squared. Let me clean this up a little bit. And so, what I'm going to do is I'm going to multiply both sides, or I'm just multiply the right side by s over s. Okay. Just to make it look a little bit nice. Okay. If we do that, and we take this s on the bottom that's already here, then we finally arrive at our Laplace transform of cosine. We get s over s squared plus omega squared. Okay. And so that right there, that's the actual Laplace transform of cosine omega t. Right, so now that we have the Laplace transform of cosine omega t, let's use equation 2 to find the Laplace transform of sine omega t. Okay. All right, so if we look at equation 2, equation 2 says that the Laplace transform of sine omega t is equal to omega over s times Laplace transform of sine omega. So we just solved for the Laplace transform of cosine omega t, and so let's just go ahead and plug that into the equation down there. So let's plug this in right here. So if we do that, we get what we're going to see is that the s's are going to cancel out. We have an s up top and s on the bottom. If we have the Laplace transform of sine omega t is equal to omega over s squared plus. So that's the real Laplace transform of sine. So kind of a tedious process, but eventually we were able to get what we needed. And these expressions themselves are not that bad. Any questions on kind of how we obtained this stuff here? All right. And so we've done a lot of examples today. So we've done a lot of examples of finding the Laplace transform. But this is the part where you all get mad at me, because I'm going to tell you that usually, when you're finding the Laplace transform, or I should say, usually when you're using the Laplace transform, you usually don't go through the whole process of finding the integral, unless it's kind of a very weird function. Okay? But the reason I'm showing you this is to kind of show you that the Laplace transform it's not magic. It's, there is a way to solve it. But, if you're actually going to be using this to solve ODEs, going through this entire integral process here, where do we start this example? We started way up here, right? Going through all of that and then having to solve, an algebra problem for a differential equation after this, it's just not very practical, right? And so remember, the whole point of using Laplace transform is to hopefully save us some work, okay? And so if you have to go through this whole process of taking integral, doing integration by parts, and then solving, system equation like this, it's not, it's not worth it. And so that kind of begs the question of, how do we actually use these? Well, if you look at all the Laplace transform examples that we did today, they're all for pretty common functions, right? So we started with a constant function, then we did an exponential function, we had hyperbolic cosine, we kind of did hyperbolic sine too, and then we had sine and cosine. These are all functions that you see a lot. And so because these functions show up quite a lot, we often like to store this information in a table. Right, so all the ones that we did today, they are tabulated, so they're in the table. And so when you're going to actually use the Laplace transforms, instead of having to go through this entire process, if you have a function that's within this table, you basically just use the table to compute. You use up the table and you look up the Laplace transform. Right, so realistically, the process that you follow is a lot simpler. So you just have a function, you look it up in the table, and then you just copy it to the table. Okay. And the nice thing about this is that it works for both the forward transform and the inverse transform. Because eventually, when you're using this Laplace transform to solve an ODE, eventually you have to transform it back into the physical domain. Right? And just like the forward transform, the most efficient way to do this is to just use it. All right, so I have the table that's copied in the notes, and so I do want to show you that, just so you know where to find it. And so next, I'll probably post homework 3 sometime next week, and so when you're doing homework 3, you're going to be using this table to basically perform. But any questions on any of this before I switch to the switch to online? Yeah.
You have to memorize?
No. So for the exam or basically anything that I'm gonna have you do in class with Laplace transform, I'll print out the table. I'll make it. I need to find it. I have a nicer formatted one, but I'm gonna give it to you so you don't have to get that. Okay. All right. So let's see where it is in the notes. And so I know you guys are still working on homework 2, but just so that you can kind of see. And I definitely should have had this open before the class. Okay, so we go to Canvas here. Click on the class. Okay, and so the notes for today's lecture is in week 4, right? So you're going to go to week 4. And then you're going to go to lecture note 03, which is on the Laplace transform. You're going to click on these notes. You're going to scroll down. Look at all the examples that we did today. And on page 5 of the notes, you can see this table. Okay. So this is the table for the Laplace transform. So you can see a lot of the examples that we did today. We have the Laplace transform of a constant function, 1 over s. We have the Laplace transform of an exponential, e to the at, that equals 1 over s minus a. Okay. We have sine and cosine. So cosine is s over s squared plus omega squared, and sine is omega over s squared plus omega squared. And we have hyperbolic sine and cosine. And so when you're doing Laplace transforms, unless the function is not in this table right here, you don't have to go through the whole integral process. You just use this. You don't have to copy this down. So the reason I'm showing you this is that it's posted online, and so it's kind of a lot of writing to do. But I wanted to show you kind of where it was. So that, oh, and people on Zoom can't see this. There you go. Sorry, Zoom people. You're looking at my iPad the whole time. Let me show you again. Okay, and so on the course website on week 4, you're going to click on lecture note 03, and then what you're going to do is you're going to scroll down. You're going to scroll past all the examples we did today, and then on page 5, this is the table right here. And so, you don't have to copy this down, just kind of be aware of where it is. And just like someone mentioned, I'm not going to expect you guys to memorize this. And so, whenever we do any in class, like midterm exams or anything like that, I'm going to give you, and so usually, how this works is that, you basically just look things up. All right, any questions on this? All right, so we have about 10 minutes left, and so I did want to do a couple examples of an inverse transform. You can kind of see what that looks like. All right, and then we're going to use the table method that I kind of just mentioned. Okay. So the inverse Laplace transform basically takes us from a function of s, and then returns us to a function of t or a function of x. So let's find the inverse Laplace. Big F of S equal to 1 over 3 minus 5. Okay. So that is our function in the Laplace domain. So we want to take the inverse Laplace to transform this back into this. All right. And so basically the game that you're going to be playing for the inverse Laplace is that you want to basically manipulate this function in order to get it to look like one of the entries in the table. Excuse me. And so it's a little bit of a, there has to be a little bit of kind of good intuition here. And so it takes a bit of time to kind of build up that intuition, because basically we're going to be trying to manipulate this in a certain way. Okay. And so if some of these don't look obvious at first, don't worry about it. It's probably your guys' first time doing these things. And so these things are, once you kind of do a few of these and do more, it kind of becomes a bit more obvious how you should manipulate them. But just for now, just kind of watch the process, and then try to use that to get a feel for how. Right. And so in particular, this equation right here, it kind of almost looks like the Laplace transform of e to the AP. If you look at the table, the Laplace transform of e to the AP is 1 over s minus. Okay. And so we don't quite have that. And so, our function here is a bit different, but, it kind of has the same form. Okay? And so kind of our logic here is that if we manipulate this function a little bit to try to get it into this form, and we utilize our properties of linearity, then we're going to be able to take the inverse Laplace using the table. So let's try to get here. Okay. So f of s is equal to 1 over 3 minus 5. Okay. All right, so first thing I'm going to do is, if we look and compare the denominator of our function compared to the table value, the s is in front, right? So the table value has s minus a. Here we have something minus s. Right? So let's factor out a minus 1. Okay. And so if we factor out a minus 1, we kind of swap the sign of the denominator. Right? So we have 5s minus 4. So that gets us closer. The other thing that we notice is that in the table value, the s, or the coefficient in front of s, is just 1, right? We don't have that here. We have a 5 in front of the s, and so we basically need to factor this out so that we can get. Okay. And so let's do this. And so let's factor out a 5 from the bottom. So we have 1 minus 1 over 5 multiplied by 1 over s. Okay, so that's good. But we need to factor out a 5 from the 3 as well. So we divide that by 5. We get 1 s minus 3/5. All right. And so we're in good shape now, because if we look at this, and we compare it to this, we can see that they're in the same form, right? So on our for our table value, we have s minus a, and so a here can be anything. So a can be any constant. Okay. And if we look at our example here, we have 1 over s minus 3/5. Okay. And so that's good. And so we're basically there. And so what we can do is we can use the table. We take inverse Laplace of this. Okay. And so if we use the table, we can see that this 1 over s minus 3/5, that is the Laplace transform of e to the 3/5 e. And then the other thing is the minus 1/5. Okay. And so because of linearity, we don't really, well, we do care, but we don't have to take it as part of the inverse. And so we just bring that just straight. And so the inverse Laplace of 1 over 3 minus 5s equals to 2 minus 1/5 e to the 3 over 5. All right, any questions on this example here? Okay, all right, so that's all we have time for today. And so on Thursday, when we pick this up, I have a couple more examples for the inverse Laplace. And then we'll actually see how this is used for the different equations. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day, and I will see you all on Thursday. Okay. I received some. I think I approved all of them. Pretty sure, but I can double check once. Yeah. Okay. Okay. Oh, no problem. I don't mind. For sure. Yeah, no, it's okay. I mean, we have the recording. Like, no problem. Exactly. Yeah. Yep, you're not doing it. It's linear, so it's just a constant. Bring it along. Yes. Yeah. Should we do on the 7th? Right. Yeah. 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 Yes. Yeah. So basically, I thought this S word was the denominator of the denominator, but I wanted to have one S here. We have to multiply by the S, so that's the thing about this. That's where yeah. Yeah.